Intrigued? Inside GM's secretive proving grounds, Chevrolet engineers made a deliberate choice to bypass domestic muscle cars and benchmark the Porsche 911 GT2 RS. The GT2 RS is a specialized German track car that held multiple production lap records at the Nürburgring circuit. They introduced an even more ambitious target, the Ferrari SF90 Stradale. The SF90 is Maranello's million-dollar flagship and 986 horsepower hybrid built for peak performance. The resulting Corvette ZR1 eventually hit the track and delivered a 2:32.3 lap time at Virginia International Raceway, officially beating the McLaren Senna's record. Virginia International Raceway is a notoriously difficult 4.1-mile road course, known for high-speed turns and steep elevation changes. This chart shows the drag strip metrics of the hybrid all-wheel drive ZR1X variant. It records a 0 to 60 sprint in just 2.1 seconds and finishes the quarter mile in 9.2 seconds, putting it ahead of nearly every gas-powered car ever produced. Hits like these require more than raw power. They require a systematic engineering solution to the physical limits that typically hold high-performance cars back. The first barrier is turbo lag. This fluid dynamic delay occurs when exhaust gases take time to travel and spin up large metallic turbine wheels. The second barrier is thermodynamics. High heat and low air density physically reduce the amount of oxygen available for combustion, usually draining an engine's power. The third barrier is simply kinetic friction. There is a hard physical limit to how much force two rear tires can apply to the asphalt before they lose grip and spin. The ZR1 and its all-wheel drive counterpart, the ZR1X, were engineered to actively manipulate these three forces. To solve for fluid dynamics, Chevy developed the 5.5-liter LT7 Gemini V8 and paired it with massive twin turbochargers from BorgWarner. BorgWarner is a specialized engineering firm that produces high-performance induction systems, and these particular turbos are the largest ever fitted to a passenger car. This schematic traces the exceptionally short air path the engineers designed. Air enters the compressor and is routed through a compact air-to-water intercooler, past the throttle, and straight into the cylinders. The car uses a specialized anti-lag strategy. When the driver lifts their foot, the computer cuts fuel and closes the wastegate, trapping the air and building high pressure against the throttle valve. A wastegate is a valve that controls the flow of exhaust to the turbo. By snapping it shut, the engineers keep the system pressurized. The millisecond the throttle reopens, that trapped pressurized air floods the cylinders instantly. This allows the engine to make full power without waiting for the turbos to spool up normally. By manipulating the movement of air, Chevrolet gave these massive turbos the immediate response typically only found in smaller, naturally aspirated engines. Next is the heat problem. Massive turbos create a significant thermal penalty. To handle the cooling, engineers had to remove the Corvette's front trunk entirely to fit the necessary heat exchangers. This graph illustrates the thermodynamic reality. As air temperatures reach 100 degrees, the air becomes less dense. Because there is less oxygen per cubic inch, the engine's power usually drops. To fix this, the computer retards the ignition timing and pushes the turbos into a 24 psi overboost. PSI is a measure of pressure, and this overboost forces enough hot air into the engine to maintain output near the 1,064 horsepower mark. By using software to override environmental variables, the ZR1 ensures consistent performance regardless of how hot the track gets. This chart compares the torque curve of the ZR1 against the base Z06. The Z06 is the high-revving, non-turbocharged version of the Corvette, and the ZR1 produces 80% more torque between 3,000 and 7,000 RPM. This is so much force that the rear tires are physically incapable of impeding traction in lower gears. To visualize that force, the ZR1 has enough wheel torque to theoretically accelerate from 0 to 60 in 3.1 seconds, while starting and staying entirely in fourth gear. This is the hard limit of kinetic friction. Two rear tires alone cannot transfer 1,250 horsepower to the ground without spinning. The ZR1X variant adds an electrified front axle to pull the car forward. This provides instant torque fill, using all four wheels to maximize the friction between the rubber and the road. Aerodynamics handle the rest. The ZTK track package features a massive rear wing that generates 1,200 pounds of downforce, using air pressure to crush the tires into the pavement. The ZTK package is an optional suite of carbon fiber aero components designed to keep the car stable at high speeds. Combining that downforce with electric torque at the front wheels solves the traction problem, resulting in that 9.2-second quarter mile. Moving beyond the hardware, we are left with a new reality. A mass-produced American car is now matching the performance metrics of the world's most expensive boutique hypercars. This has caused a visceral reaction among the elite automotive community. On luxury car forums, owners are questioning the value of their multi-million-dollar investments when compared to the ZR1's data. Supercar fan bases across Europe are facing the reality of an American car setting the new global benchmark for track performance. The ZR1 and ZR1X show that the synthesis of turbocharging and electric assistance has permanently displaced the traditional hypercar elite.